So good day guys. For now, we'll be checking on Math 101, mathematical induction to be precise. How to use mathematical induction to do is to show that a statement is true for any condition given to us. The condition can be for all natural numbers of n, for all even numbers of n, for all n greater than equals to 2, for all n greater than equal to whatsoever. It can give us condition. So what we use mathematical induction is a very powerful tool because we cannot be showing that it's true. Like we cannot show the expression for which the statement is true for all natural numbers or for any condition given. For instance, to be testing that is true for 1, for 2, for 3, for 4, for 5, it's going to take a long way and you can't even finish it because we have a lot of natural numbers. But for this particular guy, it's a powerful tool that we can conclude, that will make us to conclude that this statement is actually true for all natural numbers of n without testing all the natural numbers. Now, for instance, let's say 1 plus 2 plus 3 plus dot 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 plus n equals to n into n plus 1 over 2. Show that cos n plus 1 over 2 for all natural numbers of n. That is, n is coming from natural number. N is an element of natural number. So we have to show that 1 plus 2 plus 3 plus dot 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 till n equals to this guy. Now, we have three steps we do. The base case, whereby we say let your n equals to 1. We have the induction hypothesis, and we have the induction step. Are we together? Now, one thing you need to know now, the first step is the base case. Our base case, our base case is to showing that natural numbers is 1, 2, 3, 4, 5, 6 continuously. And we can't be showing that it's true for 1, it's true for 2, it's true for 3, it's true for 4, 5, 6. We are going to spend a lot of time, but we can just pick the first, which is 1, for n equals to 1. So let's show that it's true for n equals to 1. So we want to show that this statement is true for n equals to 1. And another thing you need to note is that for the right side, what you are doing for n is just substitution of n. You are substituting n on the right side. But on the left side, you are doing summation. Note, for this left side, you are doing summation of terms. For this right side, you are doing substitution. Now, if our n is 1, for this left side, what you are doing is the summation of the first term. For instance, if I say my n is 2, on this side, you are doing summation of the first two terms. If I say my n is 3, on this side, you are doing summation of the first three terms. But on this side, you just substitute 3 for n. If I say my n is 2, here you are doing summation of the first two terms. But here you are just substituting 2 for n. Is that clear now? Let's show that this statement is true for what? For n equals to 1. That means on this side, you're only picking the first term. Is it equal to, now, is it equal to n into n plus 1 over 2? What's our n? 1 into what? 1 plus 1 over what? Over 2. Are we together? So here we have what? We have 1 equals to 1 into what? 2 over what? Over 2. 2 cancel 2. So we have 1 equals to 1. So the statement is true. It is true for n equals to 1. The statement is true for n equals to 1, which we just showed. So we only have 3 steps to verify that it's true for all natural numbers. After this one, you don't need to be showing 2, 3, 4, 5. But for clarity's sake, let's test if it's true for n equals to 2, though which you don't necessarily need to do. Now let's just test it. If it's true for n equals to 2, show that it's true for n equals to 2. Let's just check that. And that means here you are picking the first two terms, the summation, that is the addition of the first two terms. 1 plus 2 is it equal to this when you substitute 2 for n equals to what? N, that's 2 into what? N plus 1, 2 plus 1 over 2, right? 2 cancel 2. Here you have 2 plus 1, which is 3. 1 plus 2, which is 3. So the statement is also true for n equals to 2. You cannot continue like that to check if it's true for first three terms. 1 plus 2 plus 3, that's 6. 3 into 3 plus 1, that's 12. Over 2, that's 6. It's true. You can't be checking all of. We have multiple numbers here. That's why we put dot dot dot. Even we can't write everything out because there are many numbers That's why I put dot dot dot. There are missing terms here. So it cannot be showing that it's true for all natural numbers. But how can we conclude that it's actually true for all natural numbers? Now, that's where the induction hypothesis comes in. Our induction hypothesis, why do we call it an hypothesis? Because it's an assumption. We are going to assume that this statement is true when our n is equal to k. That k can be a very big number. Like we are just assuming, let our n be a particular big number. So let's check if it's true for that big number. So if we are assuming that it's true for that big number, then we will now conclude that it's actually true for all natural number if we can show that it's true for the next number after that big number. Do you get what I'm saying? Like, we are assuming that this statement is true for n equals to a particular big number, which we are going to represent by k. Now, if you've shown the expression, for us to now conclude that it's true for all natural numbers of n, if we can now show that it's true for the next number after that big number, then it's actually true for all natural numbers of n. Now, our hypothesis, we assume it is true for n equals to k. So now, here we'll be doing summation of the first k terms. On the right side, we'll just be doing substitution of k all together. No, summation of the first k term will encompass everything on the left hand side. So here we are going to have 1 plus 2 plus 3 plus dot 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 plus our n here, you are going to represent it with k plus k equals to what? K into k plus 1 over what? Over 2. So you can't solve this further because there is nothing to solve here. You know, we have missing terms here. So this is the assumption. The fact that you've written this is that you've assumed that it's actually true because you said this, everything here is equal to this. So you've assumed that it's actually true for n equals to k. Now, for you to conclude that it's actually true for all natural numbers of n now, then you say, for your induction step, which is the last step, you have your base case, your hypothesis, and your induction step. For your induction step, whereby if true, this is how you write it. If true, no, you've assumed that it's true for k. Now, if true for n equals to k, then show that it is true. Show that it is true for n equals to what? K plus 1. If true for n equals to k, based on our assumption, then we have to show that it's true for n equals to k plus 1. If you're able to show the next number after k that is true for that, then the statement is true for all natural numbers of n. So now if we want to show now that it's true for n equals to k plus 1, on the left hand side, you are going to do the summation of the first k plus 1 terms. You know, the one we did here is summation of the first k terms. Now, summation of the first k plus 1 terms, which first of all must include summation of the first k terms. You know, k plus 1 is like a number that is 1 bigger than k. So if you want to do summation of first k plus 1 terms, at least you will need to write summation of the first k term first, then before you have the next step after k. Now, the summation of the first k term, which is this, meaning we are going to write this first, rewrite this first, 1 plus 2 plus 3 plus dot 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 plus k. Now, how do we add the k plus 1? We don't just add this k plus 1 here. What you had is the last term here, but you are adding it now in terms of k plus 1. Why did I say you cannot just add k plus 1 here? Because if the last term here is n square, you cannot just put k plus 1 here. Here you are going to have k plus 1 square. So it depends. Like you are adding the last term in the statement, but now you are replacing that n with k plus 1. So we have n here. If you have to add n back here, because now our n is k plus 1, so we have what? Plus what? K plus 1 equals to. So everything here is the summation of the first k plus 1 terms. This is the summation of the first k term with the k plus 1. Give us the summation of the first k plus 1 terms. So now, equals to n. What's our n? K plus 1 into n plus 1. That's k plus 1 plus 1 over what? Over 2. Now, if you cannot show that this side equals to this side, then we can conclude that this statement is true for all natural numbers of n. Are we together? So now let's solve this. Now you can see that for this one, it needs a replacement, because if you don't replace this, there's no how you can solve this, because we have multiple terms, like multiple numbers in between. But there's no problem with that. You can see that what we have here is equal to this guy. Because for us to have the summation of the first k plus 1 terms, we need to write the summation of the first k term first. And during our n equals to k, this is the summation of the first k term, which is same thing as this. And if this is equal to this, that means we can replace this with this, right? Do you get? So now, this is same thing as this, and if this is equal to this, that means we can replace this with this. So now I want to write this guy again, but instead of writing 1 plus 2 plus 3 plus dot 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 plus k, I'm going to write k into k plus 1 over 2, because this is same thing as this and this is equal to this. So in writing this again, I have what? K into what? K plus 1 over 2 plus, what do we have left there? We have k plus 1, right? Plus k plus 1 equals to k plus 1, k plus 1 plus 1, that's k plus 2 over what? Over 2. That should be clear now. Now, you can find the LCM here, or you multiply through by 2. Finding the LCM, multiplying through by the LCM is still the same. So let's multiply this side by 2. We can leave this right hand side and just focus on the left hand side. So if you have to multiply by 2, just like finding your LCM, because the LCM is 2. If you multiply this by 2, what do we get? K into what? K plus 1, right? Plus, if you multiply this by 2, what do you get? 2 into what? K plus 1 over what? Over 2. Just do it like you are finding the LCM is 2. 2 into 1. 1 times k into k plus 1, you get k into k plus 1. This is over 1. 1 into 2. 2 times k plus 1, you get 2 into what? K plus 1. Equals to, I'm not writing this again. I've left this. I'm only solving the left hand side. This one is there. I'm not right. So I just want to, now here we have what is common to these two. K plus 1, k plus 1. Just bring out k plus 1. What will you have left over? Here you have k left. Here you have what? Plus 2 left. Over what? Over 2. You can see that the two sides are now equal. So the fact that the two sides are now equal, now you can now conclude that the statement is true for all natural numbers of n. So you can conclude that the statement is true. The statement is true for all natural numbers of n. So now let's move to the next question. So now let's say we have 1 square plus 2 square plus 3 square plus dot 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 plus n square equals to 1 over 6n into n plus 1 2n plus 1. Now for this particular question, we have to show that this is equal to this. Show that this statement is true, that this equals to this for n greater than equal to 1. If I say for n greater than equal to 1, I'm still referring to for all natural numbers of n. Because anything greater than equal to 1, as far as counting number is concerned, is still referring to natural number 1, 2, 3, 4, 5, 6. So since it's also equal to 1, then my base case can actually start with, if there is no equal to here, if it's just for n greater than 1, then my base case will start with 2. It depends on the condition I'm given. But because 1 is included, greater than equal to 1, so my base case must start from the list. So show that it's true for n. Show that the statement is true for n equals to 1. Let's check if it's actually true for n equals to 1. So that means on the left side, you are doing summation of the first term alone, because this is just 1, like picking the first one alone. If this is 2, you are picking the first and the second term, you are adding them. If this is 3, you are picking the first, second, third, and you're adding them. But n equals to 1, you are picking the first term alone. 1 square is equal to this side. We have 1 over 6, and what's our n? 1. N plus 1, that's 1 plus 1 into 2n plus 1, 2 into 1 plus 1. So here you have what? 1 square is what? 1. Now here you have 1 over 6 into 1 plus 1 is what? 2. 2 times 1 is 2 plus 1, that's what? 3. 2 times 3 is 6. So 6 cancels 6. 2 times 3 is 6. 6 cancels 6. You can see that 1 equals to what? 1. So the statement is true for n equals to 1. Now, but we can't conclude that it's true for all n greater than or equals to 1. Before we can do that, we need to check if it's true for a particular big number k. We need to assume that. And if you can assume that, we also need to check if it's true for the next number after that big number k. Now, our hypothesis, assume that it's true for n equals to k. So, for the left hand side, you are doing the summation of the first k terms, which include everything here. But wherever you see n now, you'll be putting k. We have what? 1 square plus 2 square plus 3 square plus dot 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 plus n square. But now it's what? K square plus k square equals to, substitute your k here, 1 over 6k into what? K plus 1 into 2n plus 1. That's 2k plus what? Plus 1. There's nothing to do for that. Now, this is our assumption. We've assumed. Now, if true, since you are assuming that it's true, now you conclude that if true for n equals to k, then show that it's true for n equals to k plus 1. We want to show that it's true for n equals to k plus 1. If true for n equals to k, assuming this is greater than, ordinary greater than 1, and we start with n equals to 2, this one will be what? K plus, okay, nah, not that. This one can still be, will still be k plus 1. But if this is even number, if they say for all even numbers of n, 1 is not an even number. So here it will start with 2, and here also you will have k plus 2. Are we together? Now, we have n equals to k plus 1. So here you are going to write the first k term first. 1 square plus 2 square plus 3 square plus dot 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 plus k square plus, now to remain the k plus 1 term. This is the first k term. We are dealing with summation of the first k plus 1 term. This is the first k term. Now the k plus 1 term will be in form of the last term here. Last term in the question is n square. But now, because your n is k plus 1, you have what? K plus 1 what? Square equals to 1 over 6n. Our n is k plus 1. N plus 1, that's k plus 1 plus 1 into what? 2n plus 1. 2 into k plus 1 plus 1. Are we together? So if you can prove all this now, if you can show that this equals to this, then it is true for all natural numbers of n. Now, one thing you need to see is that this guy is equal to this guy, and this guy is equal to this, which means you can replace this with this. So instead of this now, I will be writing this. Here we have what? 1 over 6k into what? K plus 1 into what? 2k plus 1 plus, what do we have here? K plus 1 square equals to 1 over 6k plus 1. K plus 1 plus 1, that's k plus 2. Now, 2 times k, 2k. 2 times 1, 2 plus 1, that's 3. So now, we just need, you can leave this, you don't need to touch this, just focus on the left hand side and see how you can transform it to be equal to this. So we are focusing on this left hand side now. So the left hand side, let's multiply through by 6 because of we have the LCM is 6. So multiply through by 6. If you use 6 to multiply this, you get k into what? K plus 1, 2k plus 1 plus, if you use 6 to multiply this one, there will no longer have a 6 there because 6 times 1 over 6 is 1. If you use 6 to multiply this, you get 6 into what? K plus 1 square. Is that clear? So now, what are we going to do here? What do we have here that we also have here? Like, what is common to the two? K plus 1 is here, k plus 1 is also here. So factor out k plus 1. And now you have k plus 1. What will you have left here? You have k into what? 2k plus what? Plus 1. If you multiply this by this, you get this back. Plus 6 into what? K plus 1. This times this, you get this back. You know it is square here. You remove 1, there will be 1 left altogether. So here you have, don't forget there is over 6. Our LCM, there is over 6. So over what? Over 6. So equals to k plus 1 into k times 2k. You have 2k square. K times 1 plus k. 6 times k plus 6k. 6 times 1 plus 6 over what? Over 6. So here you have what? K plus 1 plus 2k square, k plus 6k, that one give you 7k. So let's factorize. What can you add that will give you 7 plus 7? If you multiply, you are going to get plus 12. You know, 2 multiplied by 6, that's 12. That's what? That's 4 and 3, right? So this one give you 2k square plus 4k plus 3k plus what? Plus 6. 4k and 3k, you get your 7k back here. Over what? Over 6 equals to what? K plus 1 into, now here you have what is common to this, you have 2k, right? Into 2k into what? K plus 2, right? um Plus 3 into what? K plus what? K plus 2. So here now, 2k times k, you have your 2k square. 2k times 2, you have your 4k. 3 times k, you have your 3k. 3 times 2, you have your 6. Divided by what? Divided by 6. We are almost done. So here now you have your what? K plus 1 into what? Here you have k plus 2 and k plus 2. Just bring out 1. You have what? K plus 2. What will be left? You have 2k left here. You have plus 3 left here. Over what? Over 6. You can see that this is equal to this. K plus 1, k plus 1, k plus 2, k plus 2, 2k plus 3, 2k plus 3, divided by 6. This times 1 over 6 is the same thing as divided by 6. So since both sides are equal, don't forget what I'm dealing with here is just the left hand side alone. Now, since the left hand side is equal to the right hand side, you conclude that the statement is true. The statement is true for all n greater than equal to 1. So that's that for that. Thanks for watching.